Hello, this is Mr. Ruby, and this is a reading of Newton's third law from the textbook. Action and reaction. Newton's first two laws of motion explain how the motion of a single object changes. If the forces acting on an object are balanced, the object will remain at rest or stay in motion with constant velocity. If the forces are unbalanced, the object will accelerate in the direction of the net force. Newton's second law tells us how to calculate acceleration, or the change in motion of an object if the net force acting on it is known. So first law, review here, an object in motion stays in motion, it stays in rest unless the force acts on it. Second law, we move in the direction of the force applied, and force is mass times acceleration. Newton's third law describes something else that happens when an object exerts a force on another object. Suppose you push on a wall. Go ahead, try it right now. I'll wait. Alright. It may surprise you to learn that if you push on a wall, the wall also pushes on you. According to Newton's third law of motion, forces always act in equal but opposite pairs. Another way of saying this is for every action there's an equal and opposite reaction. This means that when you push on a wall, the wall pushes back on you with a force equal in strength to the force you did. When one object exerts a force on another object, the second object exerts the same force on the first object, as shown in figure 13. The car jack is pushing up on the car with the same amount of force as which the car is pushing down on the jack. Action-reaction forces don't cancel. The forces exerted by two objects on each other are often called action-reaction force pair. Either force can be considered the action force or the reaction force. You might think that because action-reaction forces are equal and opposite that they cancel. However, action-reaction force pairs don't cancel because they act on different objects. Forces can cancel only if they act on the same object. So the same object would be, say, the book resting on the desk isn't moving its balanced force between gravity pulling down on it and the table pushing back up on it. It's a balanced force, one object. They cancel each other out. But in two objects, that does not how it works. For example, imagine you're driving a bumper car and are about to ram a friend in another car, as shown in figure 14. When the two cars collide, your car pushes on the other car. By Newton's third law, that car pushes on your car with the same force, but in the opposite direction. This force causes you to slow down. One force of the action-reaction force pair is exerted on your friend's car. The other force of the force pair is exerted on your car. An example of the action-reaction pair is shown in figure 15. You constantly use action-reaction force pairs as you move about. When you jump, you push down on the ground pushes up on you. It is this upward force that pushes you into the air. Figure 16 shows examples of how Newton's laws of motion are demonstrated in sporting events. Did you also know that birds and other flying creatures also use Newton's third law? When a bird flies, its wings push in a downward and backward direction. This pushes the air downward and backward. By Newton's third law, the air pushes back on the bird in the opposite direction, upward and forward. This force keeps a bird in the air and propels it forward. Visualizing Newton's laws in sports. Although it's not obvious, Newton's laws of motion are demonstrated in sports activities all the time. According to Newton's first law, if an object is in motion, it moves in a straight line with constant speed unless a net force acts on it. If an object is at rest, it stays at rest unless net force acts on it. The second law states the net force acting on an object causes the object to accelerate in the direction of the force. The third law can be understood this way. For every action, there is an equal and opposite reaction force. The first law demonstrated here shows a diver on a diving board. According to Newton's first law, the diver does not move in the straight line with a constant speed unless because of the force of gravity. So the diver comes off the diving board, going up, going up, going up, and then gravity pulls the diver down. If not for gravity pulling the diver down, then the diver should go straight off into space. The second law, as Tiger Woods hits the golf ball, and there's the golf ball right there, he applies a force that will drive the ball in the direction of that force, an example of Newton's second law. And the third law here with the gymnast, Newton's third law applies to even when objects do not move. Here, the gymnast pushes downward on the bars push back on the gymnast with equal force. Figure 17. The force of the ground on your foot is equal and opposite to the force of your foot on the ground. If you push back harder, the ground pushes forward harder. Larger and smaller objects. Sometimes it's not easy to notice an action-reaction pair is because of one of the objects is often much more massive and appears to remain motionless when a force acts on it. It has so much inertia, or the tendency to remain at rest, that it hardly accelerates. Walking is a good example. When you walk forward, you push backward on the ground. Your shoe pushes the earth backward. The earth pushes your shoe forward, as shown in figure 17. Earth has so much mass compared to you that it does not move noticeably when you push it. If you step on something that has less mass than you, like say a skateboard, you can see it being pushed back. A rocket launch. The launching of a space shuttle is a spectacular example of Newton's third law. 3 rocket engines supply the force called thrust that lifts the rocket. When the rocket fuel is ignited, a hot gas is produced. The gas molecules collide with the inside of the engine walls. The walls exert a force that pushes them out of the bottom of the engine, as shown in figure 18. This downward push is the action force. The reaction force is the upward push of the rocket engine by the gas molecules. This is the thrust that propels the rocket upward, as shown in figure 18. Gas particle, engine compartment, pushing down, then a pushing upward. Newton's third law enables a rocket to fly. The rockets push the gas molecules downward, and the gas molecules push the rocket upward. Weightlessness. You may have seen pictures of astronauts floating inside a space shuttle as it orbits the Earth or the International Space Station. The astronauts are said to be weightless, as if the Earth's gravity were no longer pulling on them. Yet, the force of gravity on the shuttle is still about 90% as large as the Earth's surface. Newton's laws of motion can explain why the astronauts float as if there were no forces acting on them. Let's look at measuring weight. Think about how you measure your weight. When you stand on a scale, your weight pushes down on the scale and causes the springs in the scale to compress. The scale pointer moves from 0 to the points to your weight. At the same time, by Newton's third law, the scale pushes up on you with a force equal to your weight, as shown in figure 19a. This force balances the downward pull of gravity on you. 19a, just stand there on a scale. The force exerted by the scale, the force exerted by the student's weight. Free fall and weightlessness. Now suppose you are standing on a scale in an elevator that is falling, as shown in figure 19b. Let's take a look at that. You're in a scale, everything's falling downward. A falling object is in free fall when the only force acting on the object is gravity. Inside the free falling elevator, you and the scale are both in free fall. Because the only force acting on you is gravity, the scale is no longer pushing up on you. According to Newton's third law, you no longer push down on the scale. So the scale pointer stays at 0 and you seem to be weightless. Weightlessness is the condition that occurs in free fall when the weight of an object seems to be 0. However, you are not really weightless in a free fall because the earth is still pulling down on you. With nothing to push up on you, such as your chair, you would have no sensation of weight. Weightlessness in orbit. To understand how objects move in the orbiting space shuttle, or International Space Station that we have today, imagine you are holding a ball in a free-falling elevator. If you let the ball go, the position of the ball relative to you and the elevator would change because you and the ball and the elevator are moving at the same speed. However, suppose you give the ball a gentle push downward. While you are pushing the ball, the downward force adds the downward force of gravity according to Newton's second law. The acceleration of the ball increases. So while you are pushing, the acceleration of the ball is greater than the acceleration of both you and the elevator. This causes the ball to speed up relative to you and the elevator. After it speeds up, it continues to move faster than you and the elevator, and it drifts downward until it hits the elevator floor. When the space shuttle orbits the Earth, the shuttle and all of the objects in it are in free fall. They are falling in a curved path around the Earth instead of falling straight downward. As a result, the objects in the shuttle appear to be weightless, as shown in Figure 20. A small push causes the objects to drift away, just as in the small downward push in the ball, and the free-falling elevator causes the drift to the floor. So Figure 20 shows these oranges seem to be floating because they are falling around the Earth at the same speed as the space shuttle and astronauts. As a result, they don't seem to be moving relative to the astronaut in the cabin. So everything's falling, everything at the same time. Alright, so that was our reading. Let me do a quick review of the highlights of what we looked at here. It's Newton's third law, action-reaction forces. This right here, we have a car is pushing down on the jack is pushing up on the car. What causes the car to move? Well, the jack is attached to the Earth, which has more inertia than the car. So the car gives to the force, and the jack and the Earth does not. Let's look at the bumper cars. You get two bumper cars. One crashes in the other. Which one is more likely to accelerate a move? It's the car with the least or the less mass. The one with the most mass in it, say you have two students in one and one student in another. The one with more mass will accelerate least. The one with less mass will accelerate more. So the less mass in the car, the more it's going to accelerate from the force applied to it. Child jumping off the side into a pool. Of course, the Earth's not going to move or noticeably move as the push is here, but the child has much less mass or inertia than the Earth itself, so the child bounces right over. Visualizing first, second, and third law. Then we have, keep in mind, as you walk, you push on the Earth. You don't notice the Earth moving because it's a very large object with lots of inertia. But you move because the force moves you, but not the planet. Rockets, interesting enough, the rocket engine is pushing gas molecules down, and the gas molecules will push the rocket up. Weightlessness, how does it work? Everything in weightlessness is in free fall. So if you're in the International Space Station, why does it seem like there's no gravity? Because you're in free fall, which causes weightlessness. And I hope you found this interesting, enjoyable, and informative. This has been Mr. Ruby, and this has been a reading of Newton's Third Law from the textbook. Thank you. Please like and subscribe.